Okay, we're moving on to higher indices. Indices, that's just the plural of index. So you need to know what an index is. So when we have a rad, whatever's inside the rad is called the radicand. That was from the first video. And then we have the actual radical here. That's the radical. And then oftentimes we'll have a number right here. A little number here called the index. Sometimes you won't see a number there, but there's always a number there in spirit. When I see rad x with no number there, this is what I mean by it's there in spirit. There's actually a 2 there because rad x with nothing there means square root. Square root. And square root of x means the same as x to the 1/2. Which means that that index could be other numbers as well. So if you have a 3, this means cube root as opposed to square root. And that is equivalent to x to the 1/3 power. And we know from exponents that, for example, 8 to the 1/3 power is 2. So that means cube root of 8 is equivalent to 8 to the 1/3. So that is also 2. That is also 2. So when the index is different, simplifying rads also becomes a little different than simplifying square roots. The principle is mainly the same. The brain takes a little bit of time to adjust because we normally don't work with cube roots or higher indices. We normally work with square roots. So let's review what we do with square roots first. When we're doing square roots, whenever we see a pair of identical factors in a square root, that's good because we know that that pair of factors in the rad is going to lead us to that factor without the rad. But that's in square root world. If we're in cube root world, then things are different. So if I have cube root of a times a or a squared, that is not going to simplify. It simplifies here because when I'm working with square root, I'm looking for a perfect square. And the perfect square consists of 2 identical factors. When I have a cube root, I'm not looking for perfect squares anymore. I'm looking for perfect cubes. And perfect cubes have 3 identical factors. 2 identical factors is not enough. In order for me to simplify, I would need something like a times a times a in that cube root. Then I could simplify that to a. But 2 identical is not enough. Okay? So as the index increases, the number of identical factors necessary in order to simplify also increases. This becomes fourth root of a times a times a times a does become a. But fourth root of just a times a, nothing. Or even a times a, nothing. You need that fourth a. Okay, so here's an example. Cube root of 16. So we're in cube root land, so automatically you must think, okay, I need 3 of something. I need 3 identical factors in that radical in order to simplify. So, what factors does 16 have? Well, if I factor it all the way down to its prime factors, there are 4 2's. And there's my triple right there, my 3 of a kind, my perfect cube. So this will lead me to a 2 with no rad, and that extra 2 must stay in the rad. And don't forget to put the index, that's very important. We are in cube root land, we are not in square root land. If something starts in cube root, we are always in cube root. And if you don't put that index, the correct index there, someone's going to read that and think it's a square root. Okay, the second one is complicated looking. And perhaps it is complicated because I haven't done it yet. Okay, so we need to factor each radicand to find out if we have enough identical factors to simplify. For the first one, we're hoping that I have 4 identical factors somewhere in 162 because I'm in 4th root. In 32, again, I'm hoping I have 4 identical factors. From 54, I'm hoping that there's something with 3 identical factors because we're in cube root. So 162, that's 81 times 2. (32) is 16 times 2. And 54 is 27 times 2. Okay, why did I factor them this way? Why didn't I break 81 down to 3 times 3 times 3 times 3? You certainly can do that, but I didn't go any further because I know that 81 is 3 to the 4th power. And since I'm looking for 4 identical factors, if I already know something's 3 to the 4th power, I know that's 4 3's. So this part is going to become 3. That 2 is going to stay. Now the second term. I know 16 is 2 to the 4th, so a 2 comes out. This 2 stays. I left 27 the way it is because that's a perfect cube. Cube root of 27 is 3, and this 2 stays. Alright, so I've taken out from each radicand as much as I can, but I'm not done because I have like terms. This guy and this guy, they are both the same type of 4th root. They're both 4th root of 2. So I can add their coefficients, 3 and 2. This is not the same type. Even though it's rad 2, it's cube root of 2, so it's different. I can't do anything with that. And there we are. Okay, last example involves a fraction, and in the last video we talked about rationalizing denominators, so you know, or you should already know, that we are trying to eliminate the radical from the denominator. But be careful here because the denominator is not square root of 25, it is cube root of 25. So in order to get rid of that radical, we have to make sure that the radicand is a perfect cube. In other words, it has 3 identical factors and nothing else. Just 3 identical factors. We can't leave anything behind in the radical because we have to get rid of the radical completely. So, I have to multiply by the cube root of something to make the product in the denominator a perfect cube. $25 is already 5 times 5. So all I need is one more 5. That'll do it. I have the 2 5s from here, and then I have a third 5 here. That's going to be 125. And we can find the cube root of 125. We know it's 5. Numerator, same thing. Denominator, 5. So the denominator has been rationalized. Okay, so that's higher indices. You just have to shift your brain into thinking, how many identical factors do I really need here to pull something out of the radical? It's not just a pair anymore. Sometimes it's 3 identical factors, sometimes 4. It could be 5, 6, 7, 8, 9, or 10. It depends on what the index is. Okay, see you next time.